Okay, so just look for that video or just start recording now. All right, so here we go. So here's the difference, is that if you're Bob, you're starting here, and you're going to go up like this, okay? So that next answer, if you look at this, well, here's 0 degrees, here's 90 degrees. That answer here, that angle has to be somewhere between 0 and 90, and probably closer to 90 degrees. So when we get into force vectors, this will make a lot more sense. So when you draw all of the forces acting on a system, it can only be one of two things. All of the forces are all balanced, and you have constant velocity, or they're not balanced and you begin to accelerate. So if you draw all the forces tip to tail, and you go dink, 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 and you draw that vector back to the origin, then that means you're at a constant velocity. So right now, all of the forces acting on you are balanced out. None of you are accelerating, okay? Because you have gravity pulling you down and you have the chair pushing up on you. Everything's in balance. Now, I won't do this, okay, because I like Hector. But if I went to Hector and I pulled the chair out from underneath him, Hector would begin to accelerate because then the forces wouldn't be balanced, okay? So, but if I draw these vectors and I end up here, if these were force vectors, then I would draw an unbalanced vector, and then that would tell me which direction the thing is going to accelerate. So when you answer that last question on that last one, what's the relationship between direction and magnitude? Here's the words that I hate and loathe, okay? Just don't say, well, the angles are going to be different. It's horrible. It's a train wreck. Stop. Don't. Okay? Different is way, way, way too nebulous. Okay? Or the angle changes. Okay? No. Stop. Okay? If you look at this, basically, they're just 180 degrees opposite. So this one is starting here and going in this direction. This one is starting here, going in that direction. So whatever you do, just don't say, oh, they're different. Oh, no, that's horrible. Okay? Or it changes, even worse. Okay. All right. Any questions on that? Yes, ma'am.
For number 10, would it be like yes or no? Because they're really like my answers are different, but they're similar.
No, there's no difference. There might be a tiny bit of difference just because of how you measured it. But, because here's the reason why. If you look at like B, C, and D, okay, so if you added vector A to the end of that and vector E back this way, all that's going to do is just cancel each other out. So, yes, you should see no noticeable difference in your answers to 8 and 9. Okay? They should basically be the exact same. Just because 3 plus 5 is 5 plus 3. Just like the additive property, you have the additive property of vectors. Okay, now, you're going to hand this in eventually, but just not right now. Okay? So what we're going to do now is that we're going to transition from using scalar quantities and protractors and rulers and drawing them all out into using trig functions where you get to use your calculator in the sine, cosine, tangent. So let me hand out the next assignment, or the next part of this, and then that will transition between the two. So don't hand in that assignment yet, but you will. Okay. 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 So if you look at this process that we just went through, the reason that I make you kind of figure out the graphical side of it is because one year we'd had a bunch of snow days, and I skipped the graphical side and I went straight to the trig functions, teach vectors. It was an absolute train wreck, okay? I had to go back, reteach them graphical addition, and then go back and teach them the trig. So that's why I have you draw this out, because that way you have an idea of, in your mind, how this deal is going to play out. It makes the trig functions make a lot more sense. So what we're going to do is we're going to now transition into how we can use x and y systems and coordinates and trig functions to get to the same results. So if you look at the vectors that you all did, okay, and initially on that sheet, we're going to use the exact same vectors that we did on the yellow sheet, okay? So here's what you got. That first one, if you were to draw that out, you would go, okay, here's my vector A, 5 centimeters at 0 degrees. Okay, that's it. Draw it out. Boom, there you go. Okay? So if I'm going to tell Bailey how to get to a certain point, this is what I would do. I would say, Bailey, you're going to start here, and you're going to walk 5 centimeters at 0 degrees. She goes, got it, Mr. Brookhamp. I'm on it. Boom. Boom. There. Boom. Stop. There. Got it. Okay? Now, Angel goes, Miss Brookhamp, man, I don't like angles. I'm more of an XY Cartesian kind of guy, you know? Okay, we can work with that too. So the other way that I could tell Bailey to get to that point is that I could give her a coordinate system. I could say, Bailey, you're going to start at the point 0, 0, and you're going to walk out to the point with a coordinate system of 5 centimeters and 0. Okay, so imagine that you're like on a number line. And here's this big, massive number line. Okay? And I'm going to tell her to walk out to an x and y coordinate system that says 5 centimeters and 0. Will she end up at the exact same point? Is 5 centimeters 0 as a x and y coordinate system the exact same point as 5 centimeters at 0 degrees? Are they the exact same point? Exact same. Doesn't make any difference. Okay? Both descriptions are equally valid. One, you're using a magnitude and direction. The other one that you're using an x and y coordinate system. So this is what I want you to see. So on vector A, you don't have to draw this out. Okay? So on vector A, 5 centimeters at 0 degrees, that's like saying the x component of that vector is 5 centimeters. Okay? And that's my x component. And the y component is going to be 0. So an x coordinate of 5 and a y component of 0 is the exact same thing as 5 centimeters at 0 degrees. The exact same point. Okay? Now, when you get to B, you have 3 centimeters at 0 degrees. Oh, okay. There's 3 centimeters at 0 degrees. I'm going to try and figure out the x and y coordinate system to get to that point. Okay, no worries. Well, I'm not going to go anywhere on the y direction. I have no movement in the y direction. So, see, my x component, there's no movement in the x direction, and it's all in the y. So on this one, I'm going to say, okay, my x component is going to be 0, and my y component is going to be positive 3 centimeters. Okay? It's the exact same thing. They're identical. You cannot tell the difference between the two. Okay? Now, where it gets tricky, and again, initially we're just going to draw these out. Okay? We're only going to do this for a couple of them because you're going to see the pattern, and then we'll move on to using trig functions. Okay? So this one I actually want you, again, this is a whole new assignment. Okay? So you're going to need another sheet of paper. So what I want you to do on this one, on vector C, whoa, that was loud. So what I want you to do on vector C is take your protractor and ruler, just like you did before. You're going to draw out vector C. So you're going to take that protractor and you're going to put it like this, and you're going to measure around 120 degrees, and you're going to draw that vector, okay, just like you did before. But the next step is then you're going to go, okay, I need to measure out how far I went in the x direction and how far I went in the y direction. So now, what you're going to do is you're going to measure, oh, how far do I go in the x? Then how far up do I go in the y to get to that same point? So make that happen. And we'll talk about what you did. And I'm going to get more coffee. So, Evelyn, can you stop that camera for a little bit? Okay, so because the fact, and we're going to go math on us for just a second. You're in the second quadrant, right? First quadrant, second, third, fourth. So since you're in the second quadrant, Jack, what's the sign of my x coordinate going to be? Positive or negative?
Negative.
What about my y component?
Positive.
Positive. Okay. So Jack, what did you get for your x component on vector C? What did you get for that value?
-2.
-2 exactly? That's cool.
Yep.
What did you get for your y component?
Uh, 3.4.
3.4? Okay. Centimeters. So here's the point. Okay? Now this one's a little bit more difficult because it doesn't lie exactly on the x and y system. Okay? So this is the bigger idea. I could either tell Jack to go 4 centimeters at 120 degrees. Okay, that's an option. Or I could tell him to walk out from this 2 centimeters and then turn and go up 3.4 centimeters. In both situations, he's going to end up at the exact same point. All we're doing is just changing the system. Do you go x, y? Do you go one vector and an angle? Okay? It's the exact same point. It's just different ways of getting there. Now, you need to do this one more time, and that's going to be that vector D. So the next one that you need to draw out, and we're only going to do 2 of these, okay? So come in here and draw, you're going to measure around, and you're going to draw a vector D, just like you did. And then you're going to measure that x component, and measure that y component. Now, right away, Izzy, what do you know about the sign of your x and y components?
They're both going to be negative
Why?
because they're both in the third quadrant.
Fantastic. Okay, so, and Lynn? Just let him in. I don't want to explain that the door's open. Is that for you? Ironically. I'm glad you're the one that went to the door then. Okay. Okay, and then fire that up. Okay, so now we've deconstructed the vectors. So here's the culminating thing. So I want to work number 5 down below. We're going to add vector A plus vector D. So let me kind of give you a visual of what's happening. You have 2 different vectors acting at the same time. So what I do is I'm going to make a sketch, okay? I'm just going to make a sketch so I have an idea. I'm not going to draw this to scale. I'm going to show you exactly my thought process. Oh, I have vector A and vector D. So here's my vector A, okay? I'm not drawing this to scale. I'm just making a sketch. 25 meters per second at 40 degrees. And then D is 11.4 at 270. So that's going to come down like this, okay? All I did is yesterday, I just did the tip to tail, right? And so now, when I draw that resultant, that's going to be something like this. Now, what that tells me, what this sketch tells me, is that when I get that resultant, it's probably going to be something in that first quadrant, which means that angle is probably going to be maybe 10, 15 degrees, okay? All I did was just make a sketch. It tells me where I should end up, okay? That's it. The next thing that you need to do is you need to set up this chart. I cannot emphasize this enough, the importance of setting up this chart. Here's the there's any number of promises I will make you. One promise I will absolutely swear to you is that when I teach you a process, I will always teach you the most efficient and best process right from the get-go, okay? I'm not going to teach you this and then tomorrow come in and go, oh, you can just do it in one step, okay? I will always, always teach you the best and most efficient method right from the beginning, okay? Always going to happen. So if you look on my answer sheet, okay, if you look at how I've worked out all of these problems, this is the process that I've went through because it forces you to keep things organized so you have an idea of what's going on. On the test, which is going to be on Monday, you're going to have a problem like this. And if I don't see this chart, I'm not even going to grade it. Okay, I'm going to tell you this straight up. And I'm not doing that to be cruel. I'm doing that because if you don't do this, then odds are you're going to do it wrong and it's just going to be a train wreck and I'm not going to waste my time searching through random numbers that you have written down. Okay? It's the best way to do this because it keeps things organized. So it's pretty simple. You're just going to draw a grid. And you go, okay, I'm going to take vector A and I'm going to add that to vector D. So then you just make a column that says, here's my X components, here's my Y components. It's just a visual way of doing what you all did when you drew them like X and up and down. All we're doing is just setting up a chart to keep track of it. Sigma means sum, so we're just going to add these columns together. So we're going to take 19.2 plus 0, and I think I should get 19.2. You can plug it into your calculator, but I think that's right. And then I'm going to take 16.1 plus this negative 11.4, okay, which is D's, which all I did was go up there up above. This is why you have to deconstruct the vectors first, okay? And you add these together and you get 4.7, okay? So all I did was just add these columns together. Took 16.1 plus negative 11.4, got 4.7, 19.2. Now, this is the absolute most critical step that you have to do. Take these vectors and make a simple sketch so you know where this thing is going to end up. So, again, you're not drawing this to scale, you're just making a sketch. Always draw your X component first, okay? So, I'm going to come out 19.2 meters per second, and then I'm going to go up 4.7. Now, the beauty of this is that now I have a right angle. Oh, now I can use the Pythagorean theorem. So my resultant then is going to be this hypotenuse. This is the end game, okay? The end game of this is that I end up with a right angle where I have two sides of a triangle, and then I can use the Pythagorean theorem to get the result. That's my end game. Okay, that's what this whole process is going towards. So somebody take 19.2 squared plus 4.7 squared, and then take the square root of all of that. Peyton, what'd you get?
19.8.
Meters per second. Now, am I done? Can I just put 19.8 meters per second? Connor, you shake your head no. Why?
It's a vector needs a direction.
Yeah. If I go, let's go 19.8 meters per second. Good on you. Fantastic. I have no direction. No idea where you're going. You're going up, down, horizontal, left, right, red, blue. I don't have the faintest idea what you got going. You have to give that angle. Now, again, this is where trig functions are your friend. Okay? So you're trying to find this angle. Okay? So what I would recommend is that you know the opposite and you know the adjacent. So what I would recommend is that I'd go inverse tangent of opposite over adjacent, which is 4.7 over 19.2. Okay? Hopefully everybody's cool with how you do that inverse tangent thing. So what do you get as the angle? Shouldn't be very big.
13.8.
13.8 degrees. So here's what this means. Is that we're launching a freshman at an angle of 40 degrees with the horizontal. At the same time, there's a downburst of wind that's pushing the freshman towards the ground. So the net effect of the cannon shooting the freshman out and the downburst from the wind pushing the freshman down that's the net effect. That's going to be his velocity, 19.8 meters per second at 13.8 degrees. Now, this is where your calculator is going to lie to you. It's like, oh, Mr. Burkamp, my calculator would never lie to me. We're besties. We're tight. Okay? Keep fully charged all the time, right? President of the Calculator Club. Calculator's not going to lie to me. Your calculator's going to lie to you. Okay? Don't be heartbroken. It's going to do that to everybody. Now, I want to play out a scenario. Let's just say that had been negative 19.2 meters per second and a positive 4.7 meters per second. Okay? The hypotenuse is still going to be the same. Okay? That hypotenuse is still going to be 19.8 meters per second. Now, this is where your calculator lies to you. Okay? This is why you make a sketch. So, somebody plug into your calculator the inverse tangent of 4.7 divided by negative 19.2. Tell me what your calculator says the answer is. What'd you get?
Negative 13.8.
Your calculator says the angle is negative 13.8 degrees. Calculator doesn't understand quadrants. Okay? Doesn't understand the fact that it's over there in that second quadrant, and it certainly doesn't understand vectors. Okay? So, this is why you make a sketch. This is negative 13.8 degrees, which doesn't make any sense at all. But here's the point. The angle that I need is this one. Okay? This is the angle that I need. I don't need this angle. So what I would do, if I were you all, and you're going to have situations like this where you have positive and negative x and y components, I wouldn't even worry about the negative. I would just find that angle. I'd just find it to be 13.8 degrees. But then, how am I going to get that angle on the outside? What am I going to do?
Subtract 13.8 from 180.
Yeah, I'm going to take 180 minus 13.8 degrees, and then I'm going to get that other angle. If it had been in that third quadrant, if it had been something like that, then I would add 180 degrees to it. Okay? So this is why you want to make a sketch. Okay, I'm done. So what I want handed in is that yellow sheet. from yesterday. You're done with that. Staple that to the back, or all the diagrams to the back. Please make sure that those diagrams are labeled so that I know exactly which one is which. Make sure that you've labeled your vectors so that I know which one are that. Make sure your vectors have arrows on them so I know which direction that they're pointing. Okay? So that is so here's the plan for tomorrow. We'll go over that assignment with the vectors and the trig functions. We'll review, test on Monday. That's the plan. Okay, and Lynn,